puzzle. Okay, when I go to add puzzle, I can actually trace. I can trace how many of you have watched the video, and unfortunately, right? Unfortunately, Irfan, late. Nampak? I can trace that you watch the video after the deadline. Eh? So no worries. This time I will accept it. Okay. So next time when I post the video, you have to watch before the deadline. There is a deadline here. I'll hopefully put that. And normally you will be given 2 days. 2 days to complete watch the video. And after that, I will not consider you as attending the class. So you have to look at this on time. You have to be on time. Then you'll be considered to attend the class for the particular day. Anyway, I actually uh, owe you hutang owe you one video, isn't it, for last Friday video? No worry, I will inshallah post to you, and we can proceed with the syllabus. Okay, so have you download the new slide?
Yes.
Okay, great. You managed to get the new slide, right? Close this. So today we're going to continue with uh, the first topic on the fundamentals of the electrical drives, right? So we start with a fundamental electric drive system. You can read that introduction. Yeah. When applied to machinery involves starting installation, then we have this. Uh, let me, uh, okay. Can you please mute everybody on the speaker, please? Your mic. All right, that should be okay. A typical drive system is assembled with electric motor and sophisticated control system that controls the rotation of the motor shaft. Nowadays, this control can be done easily with the help of software, so the controlling becomes more and more accurate, and this concept of drive also provides an ease of use. And so very precise, we know that nowadays we have this 3D printer, we can even build a house with a 3D printer, and you no longer need the molding and the conventional molding. We just build something, a very small scale of anything can be done through the 3D printer, isn't it? So it's very precise, so you can control, and this is achieved actually by the recent or the advancement in the electrical drive system. Okay, so this drive system is widely used in large numbers of industrial and domestic applications like factories, transportation system, in the case of rail, in the case of train, train, electric train. So we have this transportation system, buses, and we have these textile mills, fans, pumps, motors, and robots, etc. Coming to the history of electrical drive, this was first designed in Russia. It's actually from Russia by Lacobi in 1838 when he tested a DC electric machine supplied from a storage battery and propelled a boat. So this motor actually moved a boat. Even though the industrial adaptation occurred after many years, it's around 87 today, almost everywhere the application of electric drive is seen. When we talk about uh, the robot, isn't it? Now we have a robot that can imitate the human being. eh. So that shows that each part of the body, there is a small motor, isn't it, inside it? So this motor can be controlled, can move precisely, so that in terms of hands, if you talk about a robot, the hands of the robot, eh, the fingers, can precisely imitate the human being movement. So that is because of the advancement in the electrical drive. Okay, so this is the same block diagram that we have seen before. So we have this source, right? Normally come from the battery, and then we have this power modulator. This is actually the power electronics. Power modulator is actually the power electronic converter. Then we have motor, and we have load, and of course we have the sensing unit that sense the position, the speed of the motor, and then it will send back to the control unit. Right, send back to the control unit, and then of course you need to have some input from the computer, from your programming, something from the computer, from the memory. You store the memory, and then you have the algorithm in there, so that control the control unit, and then change, change the converter so that you will match the target uh, we call it reference speed, or whatever it is, reference. So actually there must be some if I can draw, for this, you need to have some reference somewhere here. Normally we do this sense unit, and there is a summation here. We have a reference. Okay, that reference can be speed or theta, position, where you want it to be positioned. Okay, so that will be the reference. Then you have plus minus, right? Okay. Next, the diagram shows the basic circuit design and components of the drive. It shows that the drive have some fixed parts such as load motor, powder motor, control unit, and source. These equipments are termed as parts of the drive system. They are parts of the drive system. First of all, we will discuss about the four parts of electrical, which is motor, power modulator, source, and control unit. So this will be discussed in our EPO 640. So inshallah, we will be covering all these four parts of electrical drives in EPO 640. Okay, for electric motors, there are various type of electric motors. The first motor that we discuss is the DC motors. Of course, we know that you have four types: shunt, wound, DC motor series, and then we have a compound, which is the combination of shunt and series motors. So we have a compound, and finally we have the more recent motor, which is a permanent magnet DC motor. And for the AC motors, there are two types of motors: synchronous motors and induction motors. The difference of these two motor is the speed of the rotor. If you talk about synchronous motor, the speed of the motor actually equals this to the speed of the rotating magnetic field. That's it. And S equals to, and R equals to an S. And the speed of the motor equals to the synchronous speed. Synchronous speed is the speed of the rotating magnetic field. And we talk about induction motor, there's always a slip, which is the difference between the rotor speed as well and the speed of the rotating magnetic field. Okay, so and normally the speed of the motor is slightly below than the speed of the synchronous speed. Sorry, the rotating speed of the magnetic rotating magnetic field. Okay. Beside of this, stepper motors and switch reluctance motor are considered as part of drive. Okay. So later on, we're going to discuss on at the end of the subject. I mean, at the end of the semester, we're going to look into the stepper motors and switch reluctance motor, the more advanced motor that we have. Okay. And then we have these power modulators are the device which alter the nature of frequency as well as changes the intensity of power to control electrical drive. Seconds, I need to move this. So if you have anything, you just give a message here. I can read the message at the other screen. If you have anything to ask me, just leave a message there, right? If you don't want to interrupt me, just write in the message box, chat box, and then I can read that. Okay, right. Power modulators again. These are again the converter. Yeah? So it change the nature of frequency, the nature of volt change, alter the nature, which is the voltage, current, or frequency, as well as changes to the intensity, power, control electrical drive. Converters, it has two parts: converters to convert currents from one type to that type. Then we also have variable impedance circuits used to control the speed. In case of induction motor, there are rotor resistant control, isn't it? We change the resistor, we change the rotor resistance so that we change the speed of the motor. Right? And then finally, we have this switching circuit. It's a part of the power modulators. Yeah. Sources, maybe single phase or three phase. That in terms of if you have connect to the NB, we have one phase or three phase. It is in Malaysia we have 50 hertz. For Thailand we have 60 hertz. For America we have 50 hertz, 60 hertz. And if you talk about aircraft, they operate at 400 hertz. Yeah? So for aircraft, the main frequency, the normal frequency, the main, because it's F main equals to 400 hertz. Okay, higher frequency for the aircraft. Okay, synchronous motor which are fed have had maximum up to 3,000 RPM for getting higher speed needed. Motors of low and medium power are fed from 400 volt supply and high ratings like 340. Last week we have seen the application of the power levels with respect to the motor power levels. Here we have looked into the traction, the I call watches, watches, your watch. Of course, they have a very microwatt power level. So that's that. Control unit. Choice of control unit depends upon the type of power monitor that is used. So it depends on the power converter that you use, then the control unit comes in. It can be very complicated where we have this computer, the microprocessor, or you can have this discrete components, traditional, conventional components, PI controller. That is a traditional or conventional controller there. These are many types of, like when semiconductor converters are used, then the control unit consists of a firing circuit which employ linear devices and microprocessors. So advantages of data drive, the control characteristics of this drive are flexible. I think you can read that. When you read this, you must add your notes with whatever ebook that that we shared with you. So now we have two ebooks, one from the Austin and the other one is Sharkawi. So if you want to look into the converter, the basic of the electrical drive, you read the Sharkawi book, ebook. Let me show you here. Just drive motor. Okay, there are two ebooks here. Sharkawi actually for the fundamental, and to look into the converter, so you look into this Sharkawi. But if you want to learn on the more on the advanced control technique, so on so forth, then you look this Austin, ebook from the Austin. This is good enough for you to read. Okay. Right. DC drive, okay, versus AC drive. So for DC drive, it has advantage in control unit, but disadvantage in motor. Right? As for the AC drive, there is an advantage in motor and disadvantage in control unit, whereby you it's hard to, I mean, it's more difficult to control the AC motor rather than the DC motor. But in terms of disadvantage, DC drive have more disadvantage in motor. Can you, uh, after this, can you quickly Google why this is put on? What is the advantage of control unit for DC drive? And what is the disadvantage of motor for the DC drive? Okay, so this is a comparison, comparison between DC drive, which is in types of separately excited DC drives, and we have the AC drive. Okay, so we have two types of control: phase control and chopper. Chopper is a back the DC-DC. It can be buck converter, can be boost converter, or it can be buck and boost. Right. So principal advantages. Oh, this is actually the slide, the following slide of the what is the advantage and disadvantage of both. Isn't it? Okay, there it's already there here. Okay, so low cost controller, relatively simple technology, good dynamic performance, relatively simple technology, and in terms of motor, there is a disadvantages whereby expensive motor for below than 1000 kilowatt, you need to do the maintenance to the brush. As I did mention last week, there is a problem with the brush for the DC motor, whereby sometimes after a few years, the brush is gone, and you won't get, you don't, there is no connection between, there is no touching of rotor and stator, so you cannot operate the DC motor. So you have to do some maintenance to the brush. And then we have low load, reduced brush life, zero torque dead band, possible failure on supply, possible instability, low motor IP rating, and the rest. Okay. And for AC drive, you can read that. You can have an induction. There are three types of motor there. Induction motor, field orientation control without a speed feedback. Okay, and position feedback. Okay, you have the control, the sensing parameter can be speed or position. This is the control parameter, can be without the speed. We have with the speed, and this is position control. Right, three types. Okay, so principal advantages of this and disadvantages. Converter required generation to supply, limited torque and speed loop correspond, additional converter required for generation to the supply, additional converter required for generation to the supply field, we can arrange it. So this is among the advantages of disadvantages of both DC and AC drive. Okay, now the we need to understand what is a force as well as the torque. This is the two main elements that move the motor. So we go back and look into what is the definition of force. Force is a push. If you force something, then actually you push an object. It can be you push your friend. It can be you push the door. It can be you push your motor. Right? It is a linear movement. Right? Linear movement. In short, force can be defined as the external agency which makes the body change state, size, position under strain. So you move the body from one position to another position, or you move, or you, if the body has been stuck into you can also move the size of the body, right? So it is denoted by F. Sir Isaac Newton actually discover this. An object continues in its state of rest or motion unless acted on by an outside unbalanced force. So if you have a, 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 a motor, which anything that is stationary, put at rest, and then you push, it will move, isn't it? Or you have a ball moving in one direction, and then you have a player, a football player, kick to the other directions, then the ball will move to the other direction. So that is a force. It is a linear motion. Force only apply for the linear motion, and it is described by F equals to m, the mass, dv over dt. So we differentiate the velocity with respect to time, and this also known as acceleration, isn't it? So this actually A is the acceleration, and therefore we have force equals to ma. Yeah? Normally it's a small, can be small or capital M there, but it is M mass multiplied by the acceleration, or in terms of equation, we have M multiplied by dv over dt. All right, so now we compare with the torque. Torque is, for example, in a car, torque is the force the piston put on the crankshaft, causing an wheels to turn. Right? So here is the defined as a twisting force. Rather than a linear force, torque is actually the twisting force. All right? Just like you open the door, isn't it? You turn the key, for example. You turn in the key, so there must be a torque. Instead of force, because it's a torque, the turning key. And also, when you uh, turn the knob of the door, eh? Pintu punya tu, right? That is the turning of the door. That is a torque. But when you push the door to open, then there must defined by two other torque. Which is for torque, we need to know that not only the mass, the weight, the mass, and acceleration of linear, but also how far that force is from the axis of rotation. So we have this axis of rotation. Okay, so we have a hinge there. So this is the hinge. Angsel. In Malay, we call it the angsel, if I'm not mistaken. Okay, there. So this is the axis of rotation, right? So we need to know the force. Force is you move with a particular phase, and then the also there is on the next slide. So we will get the different result. If we push the door at the hinge side, will make it much harder to open. So what it does says here is that we will get different result if you push close to the axle here. Let's say you push the door there, compared you push the door from there. Of course, you are more difficult. It's harder to open if you move in that direction, isn't it? In that position, compared to if you push the door from that position because of this D. Isn't it? If you measure that and compare with this D, okay, of course, you found out that this D is greater than that D. And that's why you have more torque and easy the door to be opened. So this is the definition or equation. So you have this axis of rotation just now, right? The angsel hinge. Okay, so this is your door, and you push in that direction. You push using the force, and then when it rotates, okay, so there's a delta there. So finally, the torque is defined by this equation. F, the force, the amount of force that you put in, the the sorry, the distance from the axis here, from the axis here of rotation to the force when it be applied, okay, and the angle between F and T, theta, and this gives you the final equation of the torque. Torque equals to the force, the distance multiplied by sine theta. So that gives you the torque equation. Right, so next, you can have more than one torque to open the door. For example, the current engine vehicles, every car have more than one piston applying torque to the crankshaft. So if you have a 6 piston, example, 12 pistons, 4 piston. So every car have more than one piston applying torque to the crankshaft. So the total torque equals to the sum of each individual torque. So we have T equals to T1 plus T2 plus Y. So that gives you the total torque to that particular body. Okay. For rotational equilibrium, the addition of all torques acting on an object equals to 0. So this can mean that there is no torque acting on the object, or all torques acting on the object are cancelling each other. So this is another topic we need to discuss. Okay, so just to give you some graphical explanation on what is a torque. So look at this. So if you move you to the ground, so you have this, and then the direction of rotation due to child 1 will be going up. Right? So if this child 2 move down, then child 2 will go up. So that is torque. In rotational motion, torque is required to produce an angular velocity of an object. The amount of torque required to produce an angular velocity depends on the distribution of the mass of the object. The moment of inertia, so this is J, moment of inertia is always J, is a value that describes the distributions. So this is the value that describes the distributions of the torque. It can be found by integrating over the mass of all parts of the object and the distances to the center of rotation, but it's also possible to look up the moments of inertia. The moments of common shapes. That equation again, and this is the main equation here. Torque equals to J d omega over dt. So omega is radian per second, so this is the can also have A, right? D omega, but this is direction angular direction. Okay, so we have angular velocity, torque Newton meter, and then we have moment of inertia, kilogram per kilogram multiplied by m squared, and then we have omega, which is the angular velocity. It's always radian per second, right? It's always in the unit of radian per second. Okay, so this is the first equation. Right, so this is example. So if you, I'm not sure about this angular velocity of a wheel is radian per second, but this is the equation that torque applies. We have to look back on this equation because this only describes the omega grid. But this one is the omega. So let's look back on this top example again. I'm not going to discuss that. Then this is again very similar. Angular velocity is 18 radian. So let's move on to the elementary principles of mechanics. Okay. Right. So now let's consider that we have this some object here, right? And it moves in that direction. That direction. Okay. So this is the you apply the force mass. Okay. You push the object from this angle, right? So you push towards the direction, and there is a change of positions from x1 to x2, for example. Eh? So there is a change of position, x1 and x2, and there is a distance of x, right? So there is a distance of x, and v is meter per second. It's a velocity of the moving object here. And of course, we have this F force friction because of this floor, for example, surface, there is a friction, correct? And there's a friction, and it always acts in opposite of mass force. Okay, it acts in the force. So the Newton's law states that the total force equals to Fm minus the friction force equals to m multiplied by dv over dt. And also you can have this in this equation here. Very similar equation like before, but in terms of total force, it is Fm minus Ff. Yeah? So it is a second order differential equation for displacement. Right? This is second order. First order, we consider the equation for speed. First order. Right? So that is a first order differential equation and second order differential equation for displacement. Right. Next, again, we look into the rotational motion. Just now it's a linear motion. Now we talk about rotational motion. So let's say that this is your rotor and it rotates in this direction, right? Direction of rotation. Okay. This is the torque from the motor, and this is a motor angular speed of the motor, and we can see that the load torque. This is the load torque. If you connect to the any load here, okay, there's always an opposite load torque to your electric or this this motor torque. So we have PL always opposed to the PE, just like your friction just now. And we have FR just now, isn't it? The friction. So in terms of rotational motion, we always have this load torque that oppose to the electric torque here. Okay, so we have a total torque or net torque there minus the load torque, and this equals to J multiplied by d omega m over dt. So if you have a constant J, then we have this equation again, similar as before. We have first order for angular frequency and second order for the angle position. This is a relationship between torque and speed, and we always given in terms of practical. This is Saga, isn't it? The new Saga. If you look at the specification of a Saga, Proton Saga, there's always mention about maximum torque that the engine can produce. This is produced by the engine, isn't it? So we have 120 Newton meter, and then we have this 120 compared to that. There are similar engine, if I'm not mistaken. 60 volts, yes, there are similar engine. So they produce a similar output torque, right? Similar engine, so they produce a similar output. But if you look at this, different Honda Accord, they have a different engine. Okay, different engine, dual UHD, yeah, head cam, dual head cam, overhead cam. So they produce a different output torque because of. So this is the same torque that some here. But we talk about 4-cylinder 16 valve Dodge, then it produces more torque. That's okay, right. So when we think about the rotating, the rotation of the motor, and when the motor rotates, we know that there is a torque from the motor, which is the electric torque, and we also have the torque, the load, isn't it? The load. It can be anything. Load can be the fan, can be the pump. So this load torque has a different shape. Okay, it can be many shape of load torque, many characteristic. Okay, it can be this hyperbolic, or it can be a straight line if you like. Okay. The torque, the characteristic of the load torque can be a straight line, for example. So the intersection, right? So the intersection between the load torque and the other one. So the intersection between the electric torque and the load torque give the steady state speed where the motor will rotate. So in that particular, so it will rotate close to the right? So if you drive this particular load, the motor will rotate with that particular speed. It will not rotate at that particular speed. It will not rotate at a particular speed. It will not rotate at a particular speed. It will only operate where the load torque intersect with the electric torque. Okay, so that's why for T1, uh, this is omega R, omega R2. So if you want to make sure that the speed of the motor rotate at that particular point, what need you do? What need you to do? You have to move this so that it go to that particular point, isn't it? So you have to move. Yeah? You have to somehow move this to, okay, by changing the control, isn't it? Remember, we have the control box, I mean the control unit. So that control unit will move, will change the electric torque so that it match that particular point so that you want to move at particular speed there. And so that is a concept. So you must have to have TE equals to TL. Right? So that is a fundamental. Right. And then we discuss on the stock speed quadrant operations. This is very important, whereby we need to look at to understand the operating principle of a motor. Okay, so we know that P equals to omega torque. The power, the electric power equals to the electric torque multiplied by the speed of the motor. Okay, so let's consider that we move. So okay, just Just look at this is known as a four quadrant, right? Four quadrant. This is the first quadrant, and first thing first, you have to have this speed versus torque graph there. Huh? So you plot this omega with respect to or versus torque plot. Then you have 1, 2, 3, 4. Sometimes, if you refer to a few books, they put in the top and cut here. Okay, so there's a at the y-axis we have top, at the x-axis we have this omega. So in this case, you will have first quadrant there. This will be second quadrant. That will be third quadrant, fourth quadrant. Okay, so you have to remember that if you put in the omega versus top, then this should be first quadrant, second quadrant, third quadrant, and fourth quadrant. So in the first quadrant, the torque is consider that the torque is positive. Let's say that we rotate in that direction. So the torque is in that direction, and we also have the motor also rotate in that direction. In the second, and therefore, we have P equals to positive multiplied by positive. So you have a positive power from the motor. In the second quadrant, we have this torque is negative, which means torque is reverse. The torque now is reversing, whereby you have still have omega in that particular movement. You have the rotor rotate as well, but at the same time, you the internal torque from the electric from the motor is opposed to the speed of the rotating the direction of the motor, and we have this omega there. So this is the opposite, and now we have P equals to torque omega. Torque is negative now, and omega is positive. So the result is negative. Okay, so similar happens here. We have negative torque, and we also have negative omega. So therefore, power equals to negative multiplied by negative. So we have a positive power, positive power. And the fourth quadrant, you have a opposite. The torque is positive, however, the rotor is negative, and therefore you have a positive and negative. You have a power. So this is the four quadrant of a motor. Four quadrant of the motor. You can read that. So for quadrant 1, both torque and speed are positive. The motor rotates in forward direction, which is in the same direction as the motor torque. The power of the motor is the product of the speed and torque. Therefore, the power of the motor is positive. Energy is converted from electrical form to mechanical form. So, to talk about if I can draw the motor as well as the load. Let's say this is the load, this is the motor. So the power actually flow from motor to the load. So that is the power flow. This power flow from motor to the load. The energy is converted from electrical to mechanical form, which is used to rotate the motor. The mode operation is known as forward motoring. So you have to remember this. It's always known as the forward motoring. In the second quadrant, you can read that it is known as forward braking. So you brake. Your motor rotates in that direction, and somehow you make that you have a electrical motor, electrical torque, which is opposed to that direction, the rotation of your rotor. So you want to brake, you want to slow down the rotor, and it is known as a forward braking. The next on quadrant 3, we have this energy is converted from electrical form to mechanical. The quadrant 3 in the reverse motoring. Remember, we talk about motoring in that direction. Omega M, positive is in that direction. Forward motoring. Okay, and therefore in third quadrant, so this is first quadrant. On the second quadrant, you see that the motor now reverse motoring. So it rotates in different direction. So this is known as reverse motoring. Still in motoring mode, but in the reverse opposite direction. Okay. And finally, quadrant 4, this is known as reverse braking. So this is forward braking. And this fourth quadrant is known as a reverse braking. Okay. So that is a 4 quadrant. So therefore, you have to remember, if you change the this, so this top, yeah, then 1, 2, 3, 4. So this is the reverse forward motor, the reverse forward and braking, reverse brake forward and reverse motoring and braking region. One, this is forward, this is reverse. Okay, if we change the top and omega axis now. Okay, right. So next, okay, let's look further on the this motor as well. So as I described just now, we have this. I think you can read that. This is easy to understand, as I did draw just now. So we have motoring, forward braking, reverse motoring, and reverse braking. Okay. So this is a 4 quadrant operation. This determines how you're going to control your motor. If you want to be in the fourth quadrant, because this define the whole system, isn't it? The load as well as the motor. So to determine where your quadrant, what is the operation, which quadrant that your motor is operating at particular situation. Okay, the fourth quadrant. Right. So before finally we look into the 4 quadrant operation, the practical operation of a lift system. Okay, so let's consider we have this lift system, and we have this always the cage or the lift is actually connected to a counterweight. There's always a counterweight inside the system. Okay, so we have this. Sometimes we call it as a car. The lift. So you can use that there. Right? I can draw that. Right? So this is a counterweight. Of course, let's say you put there 60 multiplied by 10, 60, 600 kg, for example. There's a it's fixed at certain, but your cage here can be 0, isn't it? If nobody inside the cage, this is, we just say we remove the weight of the cage. Let's say we start with 0 kg. If no one's in there, and then it will of course increase or reduce the rate. It depends on the cage. Okay, so we can have the weight of the empty cage lower than the counterweight, or you can have weight of full loaded cage which is greater than the counterweight. We have these two conditions here. Weight of the empty cage which is lower than the counterweight, and we have second condition whereby weight of the full loaded cage which is greater than the counterweight. So that's why it's specified the maximum weight for your cage. The maximum that is to define this, right? So another convention, upward motion of the cage is positive. So if you want the motor to move upward, then this is positive movement. If it goes to the negative downwards, this is negative, right? And for the motor, the convention is that if he rotates in the anti-clockwise, is positive speed. It operates in the clockwise, that is known as a negative torque, or positive speed or negative torque. Opposite. Positive is negative. You can have a torque as well as the speed direction. So what causes the motion? In terms of motoring, of course, we know that in terms of motoring, we have positive power, and for the braking, we have negative power pressure. Okay, so let's look at the four situation. Okay, this is the four situation, four quadrant, or four conditions that we need to consider. So first, let's have this counterweight. Okay, this cage is, we have this cage is what we call it, the weight is higher than the counterweight. Right, and of course, and you want it to move upward. Okay? You want this cage to move upward, positive direction, and of course, there is always a load torque which is opposed to your electric torque. Okay, so this is where you want to control the speed of the motor. So actually, in this condition, we have the motor operate with a forward motoring. So you can change the torque so that it moves or rotates with the same rotation of the motor. Okay, so upward. Okay, so next in the forward braking, that's where the counterweight is greater than the cage. The counterweight is greater than the cage, and now we can see that the rotation of the motor is in that direction. Okay, and now we want to do some braking. We want to slow down the cage here. We want to slow down. The cage is going upward, right? And the motor rotating direction. And if you want to brake it, so you have to apply the negative torque, so that the cage here will stop to, have some braking. So the cage there, the lift there will stop to slow down, right? So you apply a negative torque to your motor. But in terms of this third quadrant, You want to move the downward, and you want to move cage to downward. Of course, your motor will need to rotate in that directions, right? And therefore, you apply a positive torque that direction. So this is known as the reverse motoring. Hmm. So your motor now rotates in that direction instead of that direction, isn't it? Go upward. This is because the upward, now the motor rotates in that direction. In this third quadrant, the motor rotates downward. So the motor in that direction. So we need to have this electric torque similar to the that. And it's the reverse motoring. And finally, you have this fourth quadrant whereby you want the cage to move downward, okay, downward, right? And of course, you need to apply the reverse torque so that you will do some braking to oppose the movement of your motor here. So this is the four quadrant. If you can, if you want to look into the application where this is needed for the lift system. Okay, so that also can be applied to any of the system. Okay, so that's a four quadrant of the lift system. Next, again, now you look at this torque speed characteristic is in terms of before this we have omega against torque, but now you have torque against speed. It can be drawn in any direction. So we have 1, 2, 3, 4. So this is the limit. If you see the dash line here is actually the limit. And for to operate the motor in safe area, safe zone, you must operate it within that area. Eh? And this is known as safe operating area of motor. You cannot work at the limit. So you have to give some limit to your motor to work before you have below than the motor can handle. So you design, this is the maximum design that the motor can withstand. And for safe operations, we limit that. We don't apply the top at that particular maximum, but we limit to that particular so that your motor operate at the safe area so that you can operate, you can use your motor as longer as possible. You want to make it to work as longer as possible. Okay, so this is the safe operating area of motor. And finally, some exercise. So this is known as a speed characteristic of any motor. Just an example, right? So this is a speed characteristic. We draw the speed of this object with respect to time in milliseconds. So time in milliseconds, so this can be 0.01, isn't it? 1, 2, 3, 0.01, 0.025. And we know that the torque, just now we have this torque equals to J is the moment of inertia and B here the friction coefficient. B is the friction coefficient. So this is the total equation. TE minus T load equals to J T omega dt plus D omega. And you are given the constant. Say that we have a constant moment of inertia equals to 0.01, B equals to 0.1, and the load, T load is 5 meter. Okay. So what is the torque profile? is the torque needed to produce so that what is the torque profile? You want to look at the torque profile, the equation describe the torque profile here. Okay, so equation, right? So you have to have a piecewise. This you need to describe for piecewise, one by one. Okay, so this definitely 0. No, you have this 0, so you have okay. So this is that. Okay, from 0 to t 10 milliseconds. This is 0, 0. Don't see any speed. 0, 0. So this is gone. This is gone. Okay, and we have only 5 Newton meter. So here we have only 5 Newton meter of TE. Okay, for the first one. For the second region, from 10 milliseconds to 25 milliseconds, we have an equation, isn't it? This is only a y equals to mx plus c. So you need to find what is the m, the we call it uh, the slope of the line, which is in this case, this is speed, isn't it? Omega, the omega over t, isn't it? You need to find that. So that gives you this m. So this is y equals to mx. Okay, right? So you need to find this is your m, this is your c, right? So then you have this equation 0.01, which is b. Uh, this is also your slope, isn't it? So this is a slope. D omega over dt is actually the slope of this uh, characteristic here. So you just simply look at the slope. This is slope of the line. So it is 100 divided by 0.005. So that's why we have J. This is J multiplied by the slope d omega over dt. And then you have B here. So this is B multiplied by the equation omega. So this is the equation y equals to mx plus c. So how to get that? M from there to get the slope. Delta omega over delta t. 100 over 25 minus 10, 15. Okay, so that's why you have that equation plus 5 plus. So that define this zone. Next is this zone. And finally you have this zone. And finally you have another one actually. But this is nothing. So we just ignore. Let's say that we end up that point. We don't know where it's end. Okay, just ignore that. So this is the top profile. Okay? So this is known as the top profile of your whatever given object you need to drive. Okay, so that is very much the classes for today. You can try to do this. Go for Sharkawi. This is actually from Sharkawi, page 23. You can read page 236 to 268 to get further information on the slide just now, right? And you can try this exercise, right? If you want to put in 6 to get to understand more on what we have just discussed. Okay. Anything else? Anything that you want to ask? Aiman, betul. Yes. Change layout.
Tidaklah buat masa sekarang ni untuk Prof.
Oh, right, great. Okay, Amir. Okay, one question. Have you tried to use the U feature?
Yes.
Yes. Did you find there is a few slides there, isn't it?
Yes.
Okay. So download that and try to look on more. You see the folder from Dr. Nabil, Ada tak? Dr. Nabil, Dr. Rahimi. Ada?
Ada?
Okay, great. So you refer to that note, and I will add more. Anything that I'm going to use, I'm going to add more on the Google Drive, and make an effort to expand the notes, expand the lecture notes. So you cannot rely on the notes and the slides. You have to refer to the fundamental. If you want to look into the fundamental, it's the best to look into the books. Okay. So luckily we have this e-book. Just open up that and refer it. Okay. So if there is any no more questions, I'm going to post again video, inshallah, by tomorrow lah. By tomorrow, and then we're going to meet again on Friday, isn't it? Friday morning. Okay. All right. Okay, I'm going to share this meeting, this class again as usual, and you can watch it again. Okay. All right. Assalamualaikum warahmatullahi wabarakatuh. Thank you.
Thank you.
Have a nice day.
Thank you.
Prof, attendance?
For attendance.
Attendance will be based on your
You bisa juga ke?
bukan. I'm going to base on the I'm going to use Aris, but I'm going to take it based on the Edpuzzle.
Okay.
All right.
Okay.
Okay. So as we did for last class. Okay. All right. Assalamualaikum warahmatullahi wabarakatuh. Thank you.
Waalaikumsalam. Thank you, Prof.
Thank you. Bye.
Thank you, Prof. Thank you, Prof.
Okay.